Everybody, thank you for joining us today. I am Ivan Arce. I'm the CTO of Security Analysis at Quarks Lab. And with me is Alex Quint, the product manager of Quarks Flow.
Hello.
Sorry. Today we will talk about the Quarks Flow, and this is the plan for the rest of the presentation. First, I will do an introduction, about 10 minutes, about the Quarks Lab and our product, and specifically about Quarks Flow. Then Alex will talk more in detail about Quarks Flow and do a demonstration, and we will conclude with 5 minutes of conclusions and future vision for the product, and then we will open the floor for questions and answers for about 10 minutes. So hopefully we will get all of this done in less than an hour, but feel free to ask questions beyond the 10-minute limit if you want. So let's go. So first of all, a quick introduction about Quarks Lab. We're a French information security company. We were founded in 2011. Originally, it was started as a consulting company providing security services, high-value security services such as security audits, vulnerability research, reverse engineering, training in various topics, or even some security certifications as well. It grew organically since then until last year that we got investment, a 5 million euro investment in the company. Some years ago, it started, as I said, it started as a services company, but some years ago, we also started to develop security products, and we have 2 commercial products today. Quarks App Shield, which is a code and data protection software that perhaps we will talk about in some other occasion, and Quarks Flow, the topic for today, which is a file analysis platform that can be extended and it's scalable. We are quite well known in the security industry for our research work and some open source tools that we publish and technical publications that we've done, vulnerability discovers, our blog. And as of today, we have around 80 employees, 20% of which have PhDs, they are doctors. So that's a summary of our company. And what we will do today is it's an experiment. It's something that we call Demo Day, and it's our first experience with this. The idea behind the Demo Day is to show what we're working on in our product, to present you with some work and some ideas and some vision for the future, with a demo, of course, that's why it's a Demo Day, and to get your impressions, your feedback, your questions, and your ideas or your comments about problems that you think our product could solve, or that you think that it would be interesting to have solutions for. And that feedback will help us shape the direction of our product. We plan to do this periodically, every quarter. So this is the first one, and we will see how it goes. We will continue to do it over the year. And here's a quick introduction to the history of our product. As I said, Quarks Flow is a scalable and extensible file analysis platform. It was originated in 2013 when 5 European organizations sponsored the development of our initial product that was initially called IRMA. Irma, the first version was released as an open source project in 2014. It is still actively used today. It has evolved over several years, and other newer versions were released. The version 3 of Irma, which is a stable version that it's used in production today, and it's the core of our commercial offering up till last year, was released in 2019. But last year we decided that we had to re-architect the entire product and rewrite a big portion of it based on the inputs and the feedback and the experience that we gained over all these years working on it. And the idea was to re-architect it and rewrite what needed to be done to make it easier to deploy and easier to maintain and to make it easier to update and to modernize it to DevOps tools that are now being widely adopted. So that is how Irma became Quarks Flow. In the process, we also did a change of names or a rebranding of our company and our products. And what we have now, it's a file analysis platform that can be deployed on-premise, but it's also cloud-friendly. It can be deployed and run on the cloud. It provides an infrastructure that can be leveraged and extended by partners and customers through the APIs that we designed. So how do we do this, and what do we want to do with this? The problem we are trying to solve is it's very simple. We want to solve the problem of figuring out if the files transitioning through an organization are safe for using. And we want to do that through orchestration and automation. Orchestration of multiple analysis capabilities and automation of these capabilities so they can be used efficiently at scale. And we look at the problem in 3 stages. The first stage is about collecting files to be analyzed, and these files can be collected manually by users or from network traffic or from attachments in emails or submitted automatically by servers or by security analysis teams, several means. So the first problem is how do I collect all the files that I need to analyze? The second problem is I have a lot of files to analyze that I can collect from different means, but now I need to do an analysis that scales well, that can accommodate the demand, and that can rely on multiple tools to perform the analysis, because we believe that there is not a single tool that can be completely accurate and precise and trusted. So having diversity, it's necessary also because the analysis tools evolve at different paces, and there may be some tools that are specific to certain threats that are important. But then when you have a lot of tools or multiple scanning engines or several ways of analyzing files, you need to produce output based on those tools that it's usable by somebody, by humans that need to make decisions, or by programs that take automated actions and may integrate with the rest of the security environment in an organization. So those are the 3 phases that we look for in our product. And there are several use cases. These 4 use cases that we have listed are use cases of existing customers. There are customers that have analysts that manually submit files to our platform to automate the analysis that they do and to identify malware in a lot of files, or to prepare the manual analysis to do the initial tasks automatically, but then use that as input for further in-depth manual analysis. There are organizations where the actual end users submit the files by themselves because they receive attachments on email and they want to, before opening them or before doing something with them, they want to check if those files are safe. So they use a web interface to log in and upload the file and see the results of the analysis. And of course, there are cases where some automated tool submits files in real time or in bulk using the API and receives analysis afterwards. And finally, there's another interesting case, which is as a platform that facilitates incident response actions. After a breach, large numbers of files may be compromised or may be suspect of being compromised. And in order to restore operations quickly, incident response teams may want to verify or check if those files were infected or were compromised in some way that turns them into malicious files. So in that case, they may want to process a large volume of files in the shortest time possible so they can give back the files to their legitimate users and let them resume operations. So those are different use cases that we see with our platform. And now the question may be, how do we build this? What is the internal architecture of this product? And I will give you a summary here, and Alex will talk more in detail about what we're doing. So we have three components, the front end, the web UI, and the API, that is the component that receives the files to be analyzed. These files can be submitted to the platform either anonymously or with authenticated users that need to be logged in to the system. There's a client API library that can be used to automate submissions and to integrate with other tools as well. There's a dashboard-like UI to see the status of a user's submissions and the results and so on. Then, of course, there's the backend component. The backend is the one that is responsible for orchestrating the analysis and executing workflows that may include many analysis engines. It has a framework for authentication that is extensible and that can integrate with the external identity providers. It has a storage system that is scalable and compatible with some cloud storage services as well. And it's the final component. It's obviously the actual analysis props, what we call props. These are engines that perform file analysis, and they may be of different types. There may be antiviruses, there may be simple database lookups on known file reputation databases or tools that inspect the metadata of a file to produce a verdict. There may be some static analysis tools or even some dynamic analysis tools that run some files in a sandbox environment to check the behavior and to produce a report on the behavior of the file. So all these things, all these analysis props are orchestrated by our backend processing system. And that is a brief summary of what our product does. And now Alex will give you more details and will show you a bit of it. So Alex.
Thank you, Ivan.
Up to you.
So let's start with zooming in Quarks flow. So the first thing is, as Ivan mentioned, we recently re-architected completely the projects and moved from a virtual machine-based system to a containers solution. The rationale behind this change is mainly to benefit from the ecosystem of containers. Moving to containers allowed us to use Kubernetes for the scaling, and we will see that later. It will allow us to scale easily and allow to run our solution on more hardware easily. It was also a way to move to an ecosystem with a lot of cloud-ready components. Ivan talked a bit about the identity and access management system. We picked Ori, and it's a dedicated component that deal with identity, the identity issue, and allow us to to plug our system with enterprise identity provider easily, and also decouple our solution from this identity topic. We also use a storage component compatible with the AWS S3 storage system that allow to easily scale the storage part. And we will see in this demo day two main benefits from also moving to containers: the scaling and the packaging. The scaling part will be mainly theoretical, so I will explain it through the slide. The packaging, as it was something like just like Ivan said, that was quite complex with the whole version of Irma. We will show it in the demo how the moving to containers solved that issue. The first thing is that Quarks Flow is still a server-based solution to analyze files, mainly composed by three big parts: the API, the backend, and analysis. API will be the entry point for all the outside world that will deal with file submission. The backend will take care of storing the file and handling results in the database. And the analysis will be the part that will deal with all the third-party tools integrated into Quarks Flow. And we will see that a bit in detail after that. On the left, you see the various use cases. So automatic submission for servers that will automatically analyze files on a shared server or send to a mail server, for example, or the manual case where users have files that they just want to analyze to get a verdict on them before using them on their computers. And the actionable output for that, there are many actionable outputs. One of them could be reporting for an incident response team, for example. We will see more example in later on the slides. If I zoom a bit into the three components, the API will be composed by the identity and access management and the real API, the applicative API. The backend, as I just said, it's mainly the storage on the MinIO component and the database for the results. And the analysis part, it's one of the new feature in the Quarks Flow, is to use a workflow-based analysis. So all the tools that you see, it's only part of the tools we integrate in Quarks Flow, will be used in a way to optimize the resource that we have and to get the results as quick as possible. The rationale behind using a workflow for analysis are, just as I said, optimize file analysis. It also it's a good way to standardize analysis procedure and to make sure that certain kind of files are always analyzed the same way. You are using the same series of tools and taking the same decisions about files, whatever the origin of the files, whether it comes from a mail or from a download by a user. You are sure that it was analyzed the same way and the verdict is the same. Also, you keep track of this analysis in your database. If I go into the details of a workflow, so let's say a file is submitted to the API. Let's forget about the storage and the database and focus on the workflow itself. The workflow, it's exactly like programmatically when you want to do an early return. So you start with the fastest probe, here in our case, that will generally be the whitelist database. You do a lookup in this database to see if your file is part of it, and if so, you could already answer the file is safe. The workflow ends here, and you already have your result about your file. If not, you will launch a second series of analysis with antiviruses. In this case, they will deal with known threats. You will launch them in parallel. We will see a bit later what will be the benefits of using a container in this case. But for this stage in parallel, you will mainly be able to detect the unsafe file. And if not, you will continue to the next stage. The next stage will get you 3 different actionable outputs. The first one, if you continue with dynamic analysis, it means you will spend more resources on this file, but it will still be to get an automatic verdict on the file, meaning you will classify it safe or unsafe. Another kind of actionable output is to send the file to analyst tools. In fact, you will benefit from Quarks Flow automation capacity, and will send the file to tools able to produce results that will be used later by an analyst to help him diagnose if the file is malicious or not. It could also be results that will be useful for other solutions. So meaning it will be used as a pre-processing system that prepare the result that will later be used elsewhere. And the third category of the third actionable output that you could have with Quarks Flow is the sanitization. Here we are not interested by having a verdict. We are not interested by having more information. We are just interested into having a file that we could that is guaranteed without threats. For example, you could turn a PDF into a passive one by removing all the active parts and making sure that the file you get at the end is something you could use on your PC. So that's the 3 different actionable output you could have from a workflow. Now let's introduce the scaling part, the benefits for moving to container regarding the scaling. And let's start with the older version in Yerba. For this example, I will just focus on probe, but keep in mind that on these servers, you will also have an API, a database, and so on. It's just for keeping it simple. So let's say you have 4 probes, so 4 tools that analyze files that are installed on virtual machine. Your resources on the left are split in 4 for these 4 virtual machines. And let's say that the tools runs at different speed. The first probe 1 process 1 file every 4 seconds. The second 1 file every 2 seconds, and the 2 last probe, let's say they are fast probe and they process 1 file per second. What happens if I have 4 files to analyze? I will put them in queue, and at t equal O, I will have 4 files in each of these VM. After 1 second, I will have 2 files processed. After 2 seconds, I will have 5 processed. The probe 2 had enough time to process 1 file. After that, it's still going on with the fastest probe. And at t equal 4, the queue for probe 3 and probe 4 will be empty, as it's a probe that processes files every seconds. Probe 2 has processed half its queue, and probe 1 has only processed 1 file. So it means half of your hardware is idling, waiting for new files to analyze, but these new files will not come until probe 1 finished with this queue. After 4 more seconds, now probe 2 has finished, and it's only probe 1 running, so it means 75% of your hardware is idling. And if I continue, it will take 16 seconds to process all the files, meaning you are going as fast as the slowest probe in your environment. With containers, so within Quarks Flow, this time the containers will be spawned when needed, and let's say we keep the 4 same probes and we have 4 files also to analyze. T equal O, we will have the same situation. T equal 1, same situation, and here it will change a bit because next seconds probe 3 and probe 4 will have completed their queue, and we will have more resources to share between the 2 slow probes. Meaning probe 2 will be spawned, second container for probe 2 will be spawned, and a second container for probe 1 will be spawned. After 6 seconds, we have processed almost we have processed all the probe 2Q, probe 3, and probe 4Q. We only have probe 1 left, and we could spend all the resources on this slow probe, meaning we could have all the results ready after 10 seconds. That was for the scaling part. And now for the packaging part, let's it's small memories from installing IRMA. When you installed IRMA, you had to create virtual machine. Then an important part that is on the right was that you were fetching sources from Quarks Lab server, mainly the IRMA packages, the IRMA source code, and some dependencies. But after that, you have also dependencies that you fetch directly on internet. All of that was installed inside the virtual machines, and it was a bit long, but it was also complicated to install a new probe, because every time you wanted to support a new probe, in fact, it was added source code of IRMA. So it means adding a new probe meant having a new release of IRMA, and after that, creating a new virtual machine for running that code, and relaunch a full installation, because all the existing probes should be updated to the last version of IRMA. In Quarks Flow, it's still the thing that I introduced in the first slide. We want to benefit from the ecosystem, and the way to install containers and to install Kubernetes solution is clearly helped by using registries. So for installing Quarks Flow, we have packaged Quarks Flow as an Helm chart. And for those who don't know, is the package manager for Kubernetes. So you will see in the demo, how do you install Quarks Flow with Helm charts? It's quite easy. And once the installation of Quarks Flow is done, you have a running app without any probes. After that, it will be an application feature that will fetch the new probe and install them. So it means it will be in two parts, separated parts, and you have no longer the issue we had with IRMA that bundled the source code of IRMA and its probe. In Quarks Flow, it's completely decoupled. Now it's time for the demo. It's called the demo day, so we are here for the demo. The demo will be mainly on the topic I just described. So we will install a new empty Quarks Flow instance to demonstrate the Helm installation, or to highlight the easy install of Quarks Flow. Then we will add two probes from the Quarks Flow store. It's just to show that it's easy to add a probe, and it's working once you have installed some probes. After that, we will use a new feature of Quarks Flow that lets you easily add a new probe by creating a small script. First, based on Leaf, I will introduce Leaf in a few moments. And we will turn this script into a Quarks Flow probe and use it in our local instance. So let's start with the installation. So installation start, it's exactly like I said, Helm is a package manager. So the first thing will be to enter the repository address for Quarks Flow. Here I used a private repository. So I add this to the repo list. And the next step is to install the Quarks Flow package. Quarks Flow package, it's a bundle of container application that will be launched on my local Kubernetes cluster. So that's just one command. After that, it takes some time to start the container and to wait for every container to be up and running. So on the top left terminal, I will watch for the container to be ready to be used. And on the top right, I will check for the API availability. For this demo, I will connect directly to the API just to avoid adding complexity with the user management, but it could have been the same demonstration with the user management. So for the moment, the API is not answering. We were waiting for the container to be up and running. That's the case on the top left. Now it's okay, it's running. On the bottom, I just make the port forward to be able to access the API. And now on the top right, you could see that the API is up and running. Compared to the Irma installation, as everything is already pre-installed in the Docker container, there is no magic here. It's just that we are using containers that are just started and orchestrated by Kubernetes. So it's already up and running. But as I introduced, we are, for the moment, with a Quarks flow without any props. So you could not do many things with it. Let's jump to the second part where we will install probes and use it. So on the top left, I will use the API to show the available probes, meaning I will contact the store and list the available probes. So here are the probes. I just displayed the name, the category. You could find tools, metadata, antivirus, author, Quarks Lab. For the moment, we are the only probes author. And on the top right, you have the locally installed probe. So normally it should be empty. I say normally, but it's a video, so I know that it will be empty. So yes, it's empty. So now we will make some calls to install store probes inside our local Quarks Flow instance. We will start with Komodo and antivirus. So we will do the call to the API to register the Komodo probe. And we see that it appears in our local server. We will also install another kind of probe, the DIE probe, which is detect it easy, a tool that detects packer inside executable. Here we have two probes now, so it's time to check if we could scan a file. And for that example, I will scan a known virus. It's a Petya virus, so a public virus. It's just to have something visible with antivirus. So I start the scan. When I start the scan, behind the scene, what's happened is that Kubernetes will start new containers with Komodo, with detect it easy, grab the file from the storage, analyze the files, and record the results in database and return it to the user. So that's exactly what the script is doing right now, waiting for the results and displaying them. You have the results for Komodo that we have typed results. So we have the safety results that say it's unsafe, and an extra info that says the name of the threat. For each antivirus, it's a bit the same results. And for the metadata probe detect it easy, you have more information about what the tools detect inside the executable. That completes the part 2 of our demo. And so now we have used the store, we have installed probes, we have used it in our Quarks flow instance. Now let's see how we could customize it and create a new probe based on Leaf. First, a few words about Leaf. Leaf is the library developed at Quarks Lab and in open source. It's aimed at parsing, modifying, and abstracting executable formats. Here, in our case, we will focus on Windows executable. So in the changelog of Leaf, you may have seen that there are recent released in January that added PE authenticode features. So it's the digital signature you could find in the Windows executable. And in this small script, I will check this signature. And so basically, I will add, here we are at the part where I had an executable metadata results. If there is some signature, I add the signature to the results. I verify the signature. If it's not verified, I add a safety qualifier to say it's unsafe. And in both cases, whether it's okay or not, I add the results of the signature in a field verify signature. So the important thing is to just to remember that I add an unsafe result if the file, if the signature is not valid. I will try first my script locally. For that, I will take the sample that are in the Leaf repository. They are based on the Avast installer, and the first one has a valid signature. So we will find the result of the verification flags OK. We have the complete signature of the executable. So script seems to work. Now we will try with an invalid signature. It's the same executable with a modified signature. So we use it on our second sample. We already have a warning from Leaf. And we see that this time we have an unsafe result and the results, bad signature results for the verified signature. And we still. So now that we have our script, I skipped the Dockerization part, but we turned that into a proper Docker image. We fill the field corresponding to the probe into something that we call the manifest that is used in Quarksflow to register a new probe. And we use this manifest to register the probe locally in our Quarksflow instance. Once it's done, we now see that we have our Leaf authenticode probes, and we will use it as we did in the first demo to scan a file and to get the results directly from the instance. I used again the same virus. So I normally will have the two same results for the two first probes, and we'll see what happens with the signature verification that we just added. So same as before, now I have three containers to start, waiting for the three results to be ready. And then when the three results are ready, there is a correlation part that will take, that will create the verdict, and we will have the results. So here we have a bad signature. It's interesting because it's a fake signature, certainly copied from another executable. So it's a fake Microsoft signature. But with Leaf, you are able to see that it's a wrong signature, and you still have the same results for Komodo and detect it easy. So that was a quick demonstration to see how easy it's to install Quarksflow and how easy it is to install probes, I mean, independently from the source code of Quarksflow, and also to add your custom probes inside Quarksflow. And now I give back the mic to Ivan, but this time officially back to Ivan, not because I'm crashing. So Ivan.
Okay. Okay, thank you, Alex. Thank you for the demo. We have, as I said, while you were not here, we have rehearsed this many times, but obviously it did not fail in the rehearsals. It failed when we have to do the real thing. But okay, so I will talk just 5 minutes about the future plans for the product. You have seen what we're working on, and the vision that we have for the product in the future, where we are working on this vision, is on three categories or three type of things that will work on this for the future. The first one is that we think that the value of a file analysis platform at scale, the actual security value is in being able to provide security features, security analysis features at a faster pace and in a way that in timely and that it's reactive to the current situation regarding threats. So for that, it's what you saw in the demo is that we have decoupled the analysis engine release cycle from the release cycle of the backend product itself. And that should provide the ability to deliver ad hoc analysis or custom analysis props or to improve the analysis capabilities at a faster pace. And also to use the existing platform to extend its capabilities to other uses. For example, not just for malware detection, maybe to introduce props for other type of things like vulnerability detection or some other use cases that could benefit from the same scalable platform, but could produce other types of outputs. So that is a direction that we're going. We've done the initial steps in that, in this ability to decouple and to deploy custom props, not just by us, but by partners or even by end customers that could want to do their own analysis and don't have their own props. Of course, there's a lot to be done with the automation itself. The introduction of orchestration and automation and workflows bring a lot of possibilities. The first one is that what you saw as well in the demo is to optimize some metric. In this case, it was the time to get a result. We optimize the time to get a result to make it the minimum necessary to get a valid result and to use the hardware resources efficiently. But having workflows and automation, you could also use that feature or that capability to enforce certain methodologies throughout the organization to make sure that the methodology that you implement, it's used consistently all the time, every day with every file of the type that you want to analyze in a given way. Or even to have different methodologies implemented, codified in the product. One methodology for certain occasions or for certain type of files or for certain teams or for certain use cases and another one for other use cases, but not to have this in theory or as a series of guidelines, but to have them implemented in a platform that actually performs them or follows that methodology consistently and leaving a track record of what was done. And that also will help to ramp up a team quickly because it facilitates learning and facilitates adopting the policies and the procedures of an organization that is using this platform. Eventually, all of these executions, and when you perform file analysis at scale with a lot of volume, you generate a lot of data as well, and that data helps you understand what are the characteristics, what are the unique things that your organization does, and how to improve those things using actual data that you have produced. So we will work on that as well. It's part of our vision for the product. But ultimately, what this platform should provide is information that can be actionable, that can be used for something by humans or by automated systems, by other systems. So for that, there's one thing that we have identified as necessary, which is some way of correlating results for multiple different analysis engines, what we call props. Because sometimes you may get results that are conflicting, or sometimes you may get results that are partial, or in certain cases, one analysis engine may not be very precise and may produce false positives, and some other analysis engine may be better in some cases, but not all of them. So, so a way, when you have multiple analysis engines, you will also need to have a good way to understand and specify how to combine the results from all these engines to produce something that is actionable. And for that, we believe that we call that a results correlation framework. The other part or the other component that it's necessary to improve analysis capabilities is to have a good visualization, data visualization paradigm, things that let humans detect patterns or dig deeper into certain details. And there's a lot of work to be done in that area. It's a very interesting area to work in. And of course, there are other dimensions to a platform like this. Obviously, there's going to be a need for bulk consumption of results or bulk production of results or an integration with other systems. So we will work on that. And finally, the other interesting area to work and that we plan to continue in the future is to think about analysis throughout time in an organization, to provide some capabilities for doing longitudinal analysis to know how, for example, a file evolved over time since it was originally analyzed maybe many years ago or many months ago till today, to see what changed in the organization and how the platform perform across time. So all of these are the areas that are in our mind for the future of the product. We will see things that are delivered soon. You will see other things that we will work on in the rest of the year. You will see things that we will work on in the next years. It's a roadmap and a vision that encompasses several years. And that is my conclusion for today. We are working on this. You saw a demo. It's a work in progress. We plan to have a beta of Quarks Flow, a beta program of Quarks Flow in March. And our plan is to have the general release to the public in the second quarter of the year. So if you are interested in what you saw, if it's interesting to you, if you are interested in participating in the beta, there's our contact information, and please contact us. And now we can open the floor for questions, if there are any. So there is one question. Can we collaborate on the creation of props like IRMA OSS? Will IRMA OSS continue to be developed? So there's two questions, actually. The first question, can we collaborate on the creation of props? Yes, sure. Not only that, we have made it easier to develop and integrate props to Quarks Flow. So it does, as you've seen in the demo. So we believe that it will be even easier in this case. How that will be done, it's not yet defined, because obviously the props now need to be containerized. They need to be in a container, and it's going to be different than the IRMA open source version where there's a repository with everything. So will IRMA OSS continue to be developed? The older version of IRMA will continue to be open source. We have not decided if what we will do with Quarks Flow regarding open source. But the maintenance of the older version of IRMA that it's in the open source repository, we are not planning to keep maintaining it. So it will remain open source, but it's not going to be developed further. The version 2 that it's in the public repository. Another question. Do you plan a software as a service offer for Quarks Flow? Yes, indeed. We plan to do that through existing partners. Let's see. Okay. Any other questions for now? Okay. So we don't have more questions then. I think we managed to do this in less than an hour. And I thank you everybody for attending and for your patience and for your questions. And as I said, if you are interested in beta testing, contact us, and I hope to see you again in our next demo day.